Hey guys, Miss Peterson here, and welcome to AP Physics 2, Lecture 3-1, all about charge and the electric force. This is our first lecture of the unit on electrostatics, where we're going to be covering a ton of AP topics that kind of all go together, so best to do them all in one. We're going to be talking about charges and how they interact, go through Coulomb's law, which is the quantitative way that we figure out the charge, and go through conductors and insulators and different methods of charging. Okay, so before we get into all of that, what even is charge? Okay, quick review. Atoms, okay, the things that make up matter, have protons, neutrons, and electrons. Electrons are on the outside and they are negative, okay? Protons are on the inside and they are positive. The neutrons are neutral, so when we're talking about charge, we don't need to worry about the neutrons, okay? If an atom gains an electron and has more electrons than it has protons, it is going to be negatively charged. Where if you have more protons than you have electrons, you will be positively charged, okay? Now, note, because the electrons are on the outside, okay, matter can only be charged by the transfer of those electrons. Okay, that is what moves to make things charged. And then, of course, just like we have conservation of matter and conservation of energy, we have a conservation of electric charge. Okay, and the classic rules of electric force are that opposites attract. So positive and negative charges will attract and light charges will repel. Okay, so how does an object even become charged? Well, if you wanted to charge up a balloon to stick it on the wall, you would just rub it on your head, okay? Rub it on your hair. That is called charging by friction, which is also sometimes called triboelectric charging. And it's called triboelectric charging because it has to do with something called the triboelectric series, okay? So things like wool, okay, or cotton and the human body, then they tend to become positive, meaning they tend to lose electrons, okay? Where things like silicone and PVC, that's what polyethylene vinyl is, and sulfur and rubber, like the balloons, tend to become negative. Okay? They tend to gain electrons in order to become negative, meaning they have a higher electron affinity. They like electrons more than some other atoms or materials might. Okay? Now, that is one way of charging. Another way that we charge things is by conduction. So when two objects that are conductors touch, they transfer that charge, okay? Charge likes to spread out, okay? Picture if you have a bunch of negative charge on a sphere, it's going to want to be as far away from each other as possible because it's all going to repel. So if, say, we have this positive plate with all that positive charge close to it, and we touch it to a neutral sphere, okay, those positive charges are going to attract electrons in the sphere, and electrons are going to add onto there, which will remove some of the positive charge from the plate. But because that sphere lost electrons, okay, it hasn't gained the positive charge, okay? So while triboelectric charging becomes oppositely charged, when you charge by conduction, the objects have the same charge, okay? Now, another way that we will see things is charging by induction. So when a charged object is brought near a neutral object, it polarizes it, aka moves that charge to one side, okay? Then if that polarized object, say it was one object or maybe it was two spheres touching each other, okay, if they're separated during the polarization, you can be left with two oppositely charged objects, okay? And here's a little diagram of how that happens. We have neutral spheres, okay? They are neutral. Now, if you bring a charged object toward it, then we get that polarization. Okay, that charged object repels the electrons, so they gather over here and attracts the positive charge, so that gathers over there. And because they are touching, they are conducting. Okay, because they're touching there. Where if then you separate them during the polarization, they have two opposite charges. Okay, cool. Okay, cool. So let's go ahead and practice. Okay. Charged rubber rods. Okay, so we got charged rods are placed near a neutral conducting sphere, causing a redistribution of charge. Which of these depict the proper distribution? What do you think? Okay. Well, if you said diagram A, okay, that checks out. These little things are the positive charges. Sorry, they're not that clear in the picture. But the negative will repel the negative and attract the positive. Okay. Here we have positive attracting positive. That's not going to happen. Okay. Negative attracting negative, not going to happen. Positive attracting negative, yeah. And now diagram E, we do have the positive attracting the negative, but why is that one not correct? Okay. Because this sphere is not neutral. Okay, it says neutral conducting sphere, so we would need a balance of those positive charges. Okay, we would need those three positive over here for that to be the case. But since they are not there, it is not neutral. Okay. And then a triboelectric charging one. Saran wrap has a larger electron affinity than nylon. Okay, so that means saran wrap likes electrons more. If nylon is rubbed against saran wrap, which would end up with the excess negative charge? Well, electrons are negative. Saran wrap has a larger electron affinity, meaning it likes electrons more. So saran wrap would be negative. Okay. And the nylon would be positive. Okay, cool. Which brings us to conductors versus insulators. Okay, when I say conductors, think metals. And if you remember from a chemistry class, okay, metals have these positive ions flowing in a sea of negative electrons, okay? And they are free to flow, okay? They flow freely from particle to particle, and the electrons can go wherever they want within the substance, okay? For example, in this metal, okay, the charge will spread out all along the surface because it's a conductor and it can move. Now, because everything repels each other, that charge will repel and only reside on the surface, okay? So if you have a big metal sphere, all of the charge is going to be on the outside of that sphere, meaning no net electric field in the middle, okay? Now, when two conductors touch, that charge gets spread out between it like it was just one conductor. And yeah, just think metals, tap water is very conductive, things like that. Now, insulators are a little different. Insulators impede the flow of electrons, but this doesn't mean that they can't become charged. Okay, if you have a really charged object and you touch it to an insulator, it will transfer some of that charge. The only difference is it will stay in the location it was transferred to. Okay, it would look kind of like this image, okay, where all of that charge stays in one place. It's stuck on whatever atoms or molecules were there to begin with. Okay, rubber is a good example of an insulator. Glass, dry air is a very good insulator. Okay, so that's the general properties. And of course, this is a range where everything falls within the range. Okay, now a couple other ways that charges move is through grounding. Okay, so grounding is the removal of a charge. Okay, so this means that taking it to neutral. And that's because we think of the ground as an infinite reservoir of electrons, okay? And since it is an infinite reservoir, there's tons of electrons there and available, it can add or remove, okay? If you touch a grounding object to a positively charged object, it's going to add electrons, okay? So if positive, okay, it will add electrons, okay? Where if it's negative, it will remove it, okay? For example, we can also use this to charge things. Here we have an ebonite rod that is negatively charged being brought toward a metal sphere, okay? And right now this is neutral but polarized, okay? Now, if we touch the grounding wire on it, okay, that is a wire. It is a conductor, okay? Meaning those charges are free to move. So those negative charges are going to get repelled by that negative rod and go to the ground, okay? And then if we remove the grounding wire, we could be left with a net positive charge, okay? Just by using the grounding while it's polarized. And just a little note on being polarized, both conductors and insulators can become polarized. It's just the scale to which they do it. Okay, so conductors are going to have a lot more separation of charge because those charges can move freely. Okay, as you can see in, Okay, so as you can see in this picture, both conductors and insulators can become polarized, but in a conductor, the whole charges can move, okay? They can move between the atoms and molecules that are in the substance, creating an entire net negative charge over here and net positive charge over here. Where for insulators, the polarization happens on the molecular level, okay? Polarized on molecular level, meaning within the molecules themselves, we have that separation of charge, which results in a net difference in the charge on the two sides of that insulator, but it's not as dramatic as with the conductors. Okay, cool. Now, let's get to the math stuff, okay? Coulomb's law. So Coulomb's law is the force between two charged objects. And when we look at it, we're going to be talking about the charges on electrons and protons. Okay, we use the letter E for that, where E is the elementary charge. It's the basic unit of electron charges. There are no charges smaller than it, and all charges have to be a multiple of E. Okay, charge is quantized. You can't have half an electron's worth of charge, okay? Now, it's in units of coulombs, and we use the variable Q for charge, a lowercase q, not to be confused with the capital Q that we use for heat energy, okay? Now, 1 coulomb is a lot of charge. You need 6.24 times 10 to the 18 electrons to have 1 coulomb. Most of our measurements of coulombs will be on the order of 10 to the negative something, okay? Now, on your equation sheet, on your AP Physics 2 equation sheet, Coulomb's law is written like this, okay? The absolute value of the electric force vector equals 1 over 4 pi E naught, okay? Now, E naught is the permittivity of free space, okay? And we often will not use that at all. We'll use the Coulomb's constant K, which is equal to 1 over 4 pi E naught, okay? So we have that. And then they actually have it in absolute values, where you have Q1 times Q2 over the distance between them squared, okay? They set it as an absolute value because the tendency is to think that if it's negative, if you have a negative force, that means repel. But if we look at the equation, okay, if we had a negative charge and a positive charge, that would result in a negative number. And we know that a negative charge and a positive charge are opposite. They will attract each other, okay? Where if both of these charges were positive, or if both of them were negative, we would get a positive force. So that means repel, okay? And I think that is kind of confusing because I think negative normally means repel. So that's why I say use the absolute value, okay? Use the absolute value. and the idea that opposites attract to figure out the direction rather than trying to use something like this, okay? And the form that I write Coulomb's law in most often, okay, is just that force as K, Q1, Q2 over R squared, okay? Oh, and R, of course, is not really the radius, but it is the separation distance, okay, between those two charges. Okay. And again, this K is a constant. It is Coulomb's law constant, 9 times 10 to the 9th, Newton meter squared per Coulomb squared. But on your equation sheet, it is written as 1 over 4 pi e naught in terms of the permittivity of the free space, which basically is how well the space can hold an electric field. And just so you know, I've never seen a value for it that is not this number, okay? So just use that one for all purposes. Let's look at an example, okay? So we are considering the proton and the electron in a hydrogen atom, okay? So they're separated by a Bohr radius, which is 5 times 10 to the negative 14, which is cool because then, like, you know, we actually have the radius in what we want. Yep. Or it's the radius, actually, R, times 10 to the negative 11 meters. Now, for the charge on a proton and an electron, they're equal to each other. So Q proton equals the negative charge on the electron, negative Q electron, and they are both equal to that fundamental charge, 1.6 times 10 to the negative 19 coulombs. Okay. So what is the electric force between them? We have our equation. Our equation is that the electric force equals K times Q1 times Q2 over R squared. And like I said, ignore these signs, okay? This is going to be an attractive force. Okay. So that's why I'm not going to put the signs of those charges into here. I know that it's attractive. Okay, the sign of it just tells me that direction of that force, or the type of charge, but yeah. Okay, so plug in my numbers. K is 9.0 times 10 to the 9th Newton meter squared per Coulomb squared times Q1, which is 1.60 times 10 to the negative 19 coulombs, the charge on a proton, times the charge on an electron, which is negative 1.6. But again, if I'm just calculating the force, easier to just do it with the absolute values, divided by the distance between them, squared. Okay, and then we got to be able to plug that all into our calculator. Okay, now calculators get very confused when doing scientific notation in order of operations, so I highly recommend you use your exponential notation button or your EE button, your EXP button, so that your calculator knows to treat each of these as one whole number. And then you can do the calculation all at once. So I have 9 times 10 to the 9th times 1.6 times 10 to the negative 19 times 1.6 times 10 to the negative 19. I went ahead and put all of that in parentheses. Again, I am using that EE button. Okay, so, and then divided by 5.0, times 10 to the negative 11 squared. Okay, I highly recommend putting that one in parentheses. Okay, see if you guys can see that. Okay, so that they know that the square applies to the 5 times 10 to the negative 11, not just the 10 to the negative 11. Okay, and I press enter and I got 9.216. Okay, so I'll just say 9.22 times 10 to the negative 8 newtons. Okay. And the units work out. Coulomb squared, coulombs, meters squared with the meters squared. We're left with units of newtons. Now, I'm asking you about the gravitational force. which, did this equation look a little familiar? Okay, it is almost identical to the gravitational force equation, okay, which is just a different constant, the gravitational constant g, times the two masses over the radius, okay? They have very similar equations. What is the difference between these two forces? There are, quick side, there are 4 fundamental forces in physics: nuclear strong force, nuclear weak force. We only deal with those when we're dealing with nucleuses, so we can ignore them. Our main 2 are gravitational and the electromagnetic. These 2 equations, okay? But there is a fundamental difference between them. Does gravity ever repel? The electric force can attract or repel, but in our experience with gravity, gravity only ever attracts. We've never seen an instance where 2 masses will repel each other. Now, for the masses and g, those can be found on your AP Physics 2 reference sheet, okay? So I'm just going to look at that reference sheet to plug them in, okay? We have g, which is 6.67 times 10 to the negative 11, okay? Newton kilogram squared, Newton meter squared over kilogram squared, times the mass on a proton, which is 1.67 times 10 to the negative 27 kilograms, times the mass on an electron, which is 9.11 times 10 to the negative 31 kilograms, divided by the distance between them, squared. Okay. And we plug that into our calculators. Times 9.11 times 10 to the negative 31 divided by 5.0 times 10 to the negative 11 squared. And just by looking at the constants, the K versus G, and those relative masses, we can tell that this number is going to be much smaller. And in fact, it is much, much, much smaller. 4.06 times 10 to the negative 47 newtons. Okay, so order of negative 8 versus order of negative 47. Okay, if we look at the ratio between those 2 forces, oops. Okay, so if we have that 9.22 times 10 to the negative 8 newtons over, okay, just to see how dramatic this is. Okay, the electric force is 2.27 times 10 to the 39 times larger than the gravitational force, okay? To the 39 times. That is huge. So, okay, when considering the electric force between 2 objects, we do not need to consider the gravitational force between them, okay? When considering the electric force between 2 masses, we can ignore the gravitational force between them. Okay, because, it is so, so small. Now, this doesn't mean we ignore the gravity acting on the object. Okay, gravity is still exerting a force on that object. And we will do problems where you have to balance out the force of gravity down on an object between Earth and the object with an electric force between an object above it. That's how the Millikan oil drop experiment worked. Okay, but if you're balancing out those 2 forces, you're not considering the gravitational force between that mass and the mass above it. Okay, you would consider the gravitational force between the object and Earth, but not the gravitational force between those two objects. Okay, because really it's not going to affect it at all. If I wanted to solve for the acceleration due to that electric force, okay, acceleration would be equal to the electric force divided by the mass of the electron, where here we'll do it as that force of gravity divided by the mass of the electron. So on the acceleration due to the electric force would be 9.22 times 10 to the negative 8 newtons divided by the electron's mass, which is 9.11 times 10 to the negative 31 kilograms. And we'll compare that to the gravitational acceleration, okay, which is 4.06 times 10 to the negative 47 newtons divided by 9.11 times 10 to the negative 31 kilograms. So let's go ahead and calculate those out. And for due to the electric force, we have 1.01 times 10 to the 23rd meters per second squared, so very, very, very fast, versus okay, 4.46 times 10 to the negative 17. Okay, so we can tell that this number is the acceleration due to the electric force is much, much, much greater than the acceleration due to gravity. Okay, that is why we can ignore the acceleration due to gravity. Okay, cool. Okay, cool. Now, let's get into force addition. Okay, anytime we have more than two charges, we're going to do, this is basically vector math, okay? A little review of vectors, but if we, but just using the electric force. We're going to do one here where it's just charges in one dimension, and then we'll do one here where we have to break the vector down into its components to solve it in 3 dimensions, okay? So first one, we'll do this one right here. We have 3 charges lie along the x-axis, okay? So we got the x-axis here. Zoop. The positive charge Q1 of 15 microcoulombs is at x equals 2, okay? So x equals 2.0 meters, and we have on there, okay, Q1, which has a charge of 15 microcoulombs. Do you remember what micro is? Okay, micro is times 10 to the negative 6. So Q1, you can write it as 15 times 10 to the negative 6 coulombs. Okay. And then the positive charge Q2 is at the origin. Okay, so over here at 0, we have Q2, which is another positive charge. It is 6 times 10 to the negative 6 coulombs. And then it's asking, where must a negative Q3 be placed on the x-axis so the resultant net force is 0? Okay, so we're wanting to know where to put this on the axis so that the net force is 0. Well, first let's think about how it's going to interact with both of these charges. It's negative, so it is going to be attracted to both of these. Now, if we want it to be attracted to both and we want the resultant net force to be 0, we're going to need to put it in between them, okay? So we know that this charge must be somewhere in between it. But we can do even better than that, okay? Since Q1 is stronger, it's going to attract it stronger. If it was closer to this charge, it would feel a stronger attraction to this and a weaker one to this due to both its charge and its distance. So we know that Q3 actually needs to be closer to the smaller charge, okay? So that it can receive an equal force from that one as it does from this larger charge. So let's go ahead and narrow that down. Draw that line back in. Okay, we'll put 1.0 meters here as that middle mark. and we know that it must be closer to Q2. Okay, so for right now, I'm just going to put Q3 right there so we can look at the forces on it. It's going to be attracted to this one and attracted to that one, and we want those forces to be equal. Okay. Actually, yep, there we go. So for our force, we want the force of 1 on 3 to be equal and opposite to the force of 2 on 3. Okay. So when we set up that equation, what we're going to do is say this distance here is x, to charge 3. How could we talk about this distance here so that we have less variables? Well, we know Q3 is at 2, so this would be equal to 2 minus x. Okay? Then that distance x would give us where Q3 needs to be placed on the x-axis, so that resultant net force is 0. Okay? Let's go ahead and start setting up our equation. Force of 2 on 3 will be equal to k times Q1 times Q3 over the distance between them, x squared. Where for F1 on 3, we'll have k times, this was 2 on 3. 2 on 3, this one is force 1 on 3, so Q2, Q3 over 2 minus x squared. Okay? Does it matter that we don't know what Q3 is? Nope, not at all. It's going to affect the force on both of them equally. So we can cancel out Q3. And we can also cancel out K because it'll just divide out. So our equation simplifies to Q2 over X2 equals Q1 over 2 minus X. Let's go ahead and put in the actual numbers and start doing that algebra. So for Q2, we have 6 times 10 to the negative 6 coulombs over X squared equals Q1, 15 times 10 to the negative 6 coulombs over 2 minus x squared. Okay, let's make our math even easier. We can cancel out the times 10 to the negative 6. Okay, so, and I'm also going to cross multiply so I don't have a fraction. So my equation becomes 6 times 2 minus x squared equals 15 times x squared. Okay. Now, let's work smarter, not harder. Let's go ahead and combine our like terms. So I have, I'm going to put the x's on one side and divide the 15 to the other side. So we have 6 divided by 15, which is 0.4, equals x squared over 2 minus x squared. Okay. Easiest way to solve this is going to be to take the square root of the whole thing. So the square root of 0.4 is I thought it was 0.2. It is not 0.2. Okay, it is 0.632 equals x over 2 minus x. Okay, so then do more algebra. 0.62 times 2 gives us 1.26 minus 0.632x equals x. We add the 0.632 x to both sides, which gives us 1.26 equals 2.632x. So x equals that 1.26 divided by 2.632, which is 0.48. And I feel like, I'm not going to lie, I feel like I messed up on my math somewhere. But 0.48 meters, that is in our range, so it is what we expect. But I feel like I got 0.78 last time. I figured out where I went wrong. Okay. 1 plus 0.632 is 1.632 x. So the answer is 1.26 divided by 1.632. There we go, which is 0.772, so 0.77 meters. Okay, so this should be placed at 0.77 meters. Okay, cool. Now for the trigonometry problem. Okay, consider 3-point charges of the right triangle as shown, where Q1 is 6 times 10 to the negative 9 coulombs. Q2 is negative 2 times 10 to the negative 9 coulombs. And Q3 is 5 times 10 to the negative 9 coulombs. The distance between Q1 and Q2 is 3 meters, and between Q3 and 4 is 4 meters. And we're going to find the force of 1 on 3, as well as the force on 2 on 3, as well as the resultant force. Okay, so basically, we got this charge here. It is going to be repelled by this charge. That's the force of 1 on 3, which we see in that direction. And it's going to be attracted to this one. Okay, so that's going to be in that direction. So we can picture that that net force is going to be somewhere in this direction. Okay, but we need to find what it's actually going to be. So first, let's go ahead and just find those forces. Okay, starting with the force of 1 on 3. Okay, we got K, 9 times 10 to the 9th Newton meter squared per Coulomb squared, times Q1, 6.00 times 10 to the negative 9 coulombs, times Q3, 5 times 10 to the negative 9 coulombs, divided by the distance between them, squared. So when we solve that out, we get 1.08 times 10 to the negative 8. So the force of 1 on 3 is 1.08 times 10 to the negative 8. And then let's go ahead and do the force of 2 on 3. Okay. Newtons, which is 9 times 10 to the 9th times Q1 or Q2. And again, I'm just going to use the absolute values here and then do the directions at the end because I think that's easier. Times 10 to the negative 9 coulombs divided by 4.00 meters squared. And we plug that into our calculators. Divide by 16, and we get 5.625. Okay, so I would say 5.63 times 10 to the negative 9 newtons. Okay, so we have our forces. And then I'm just going to go ahead and draw, or we'll just zoom in on that here so you guys can kind of see how that works. Okay, the force of 2 on 3 is already in the horizontal component. But the force of 1 on 3, we are going to break down into its components. Okay, so we know this angle here is 36.9, okay, because we know this angle here is 36.9. And again, that comes from setting the tangent, or we'll use the tangent of that angle equal to 3/4. So then it's the inverse tangent of 3/4. Yep, which gives you 36.9. Okay, 36.9 using those complementary angles. So we're going to break it down into its components. Okay, so I'm going to call this first one, okay, the force of X for 1 on 3. Okay, that one in the X direction, that is the adjacent side. So it's going to be equal to the force, 1.08 times 10 to the negative 8 newtons, times, it's the adjacent, so the cosine of 36.9. Okay, and again, cosine of this comes from cosine of 36.9 degrees is equal to x over that force of 1 on 3. So if we're solving for that x component, you can see how that math works out. So that comes out to, make sure your calculator is in degrees mode, times the cosine of 36.9. Okay. And I got 8.64 times 10 to the negative 9 newtons. Now we'll do the y components, Fy of 1 on 3. 1.08 times 10 to the negative 9 newtons. And now it'll be the sine, okay, because now it's the opposite angle that we're talking about, of 36.9 degrees. We plug that into our calculator. And we get 6.48 times 10 to the negative 9 newtons. Okay. So let me go ahead and zoom in and draw what we have so far on Q3. Okay, so we have Q3 and we broke it down into its components. So we have the x component of force, the x component of force 1 on 3, which is 8.64 times 10 to the negative 9 newtons. Okay, we have the force due to 2 on 3, which is 5.63 times 10 to the negative 9 newtons. And then we figured out that upward or y component of this to be 6.48 times 10 to the negative 9 newtons. So in order to get the resultant force, first I'm going to combine the horizontal components, okay, and then set up a new triangle with that. So they're in opposite directions. So I know this one is bigger, okay, the force due to x on 3, the x component of the force of 1 on 3, which makes sense. The force on 2 on 3 is a lot smaller because it's a much smaller charge. So we're going to subtract that. 8.64 times 10 to the negative 9 minus 5.63 times 10 to the negative 9. And we get 3.01 times 10 to the negative 9. Since this force is bigger, it's going to be in that direction. Okay, so let me go ahead and draw that a little clearer. Okay, there, this is our Q3. And now we figured out that the x component of that force was 3 times 10 to the negative 9 newtons. So these are the x and y components of that force. To figure out the resultant, okay, we would line them up tail to tip, okay? So if I take this one, and I'm going to move it over there, okay? And then we will be solving for this angle right there, okay? And in order to do that, we use Pythagorean theorem. A squared plus b squared equals c squared. Okay, so our resultant force, okay, is going to be equal to the square root of 3.01 times 10 to the negative 9 squared plus 6.48 times 10 to the negative 9 squared. Okay, and we take the square root of that to get our resultant force times 10 to the negative 9 squared plus 6.48 times 10 to the negative 9 squared. And then we take the square root of that answer to get 7.14 times 10 to the negative 9 newtons. Okay, so the force of 1 on 3, the net force would be that. Okay, and now if we wanted to find the direction of that force, okay, let's go ahead and look back here on the picture. Okay, we know the force is going to be somewhere in that direction. Okay, or actually, no, probably not, because we found that this component was stronger than this one. Okay, it had more in that. So actually, we expect that net force to be somewhere in this direction, okay? Now to figure out what it actually is, we need to find this angle here. So to find the angle, I'm going to use tangent. So the inverse tangent of the opposite, which is 6.48 times 10 to the negative 9 newtons, over the adjacent, TOA, times 10 to the negative 9 newtons, to get 6.48 times 10 to the negative 9 divided by 3.01 times 10 to the negative 9. Okay, and then I'm going to take the inverse tangent of that number to get 65 degrees. Okay, so that, based on how I drew it, would be 65 degrees above horizontal. Okay, so this angle here between it and the force, okay, it's probably up in this direction then somehow. Yep, okay, that does make sense. And this angle would be 65 degrees. Okay, cool. That is a big, heavy, complicated vector math problem using electrostatic charge. Okay, now you're unlikely to see something that complex on the AP exam, but you might see pieces of it, so it's helpful to understand the concepts. Okay, cool. Okay, cool.